Okay, so let's get going. Let me remind you where we were last time. So we had two definitions of consistency. So we said that a set of formulas sigma is consistent if, so that was our definition, for no alpha, sigma proves alpha and sigma proves not alpha. And we had a claim that this is equivalent to another definition that doesn't have a special role for the symbol for negation. Because we said, since we are talking completely syntactic, about the syntactic aspects, there is no special role of any special symbol. So it's kind of aesthetically unsatisfying. So we have this claim that sigma is consistent if and only if for some alpha, sigma cannot prove alpha. This is a nicer definition in the sense that it is complete. It doesn't depend on a specific choice of connectives. We could use any set of connectives or any language. It doesn't depend on having this sign inside our language. Okay, so let us show that these two are equivalent. So to show that they are equivalent, we have to prove implications in both directions. So proof both directions are pretty easy. Assume that the first definition holds for no alpha does sigma prove alpha and sigma proves not alpha. So in particular, pick any alpha, say alpha is the variable p, doesn't matter. Either sigma does not prove alpha, or if it does, then sigma does not prove not alpha, because it cannot prove both. So in any case, we found some beta such that sigma cannot prove beta. So if sigma satisfies the first definition of consistency, it definitely satisfies the other. In some sense, the first one says the set for every formula that I can prove, there is one that I cannot prove. The second one only says there is one that I cannot prove. So it's no surprise that the first one implies the second. So it's just a matter of focusing and realizing what each of them is stating. So what are we still missing? What should we do now? The other direction, right. So assume now that for some beta, sigma does not prove beta. Now pick, we have to show that for any alpha it cannot prove both alpha and not alpha. So pick any alpha. If the first definition is violated, okay, let's pick alpha afterwards. If the first definition is violated, let's start here. If the first definition, then for some alpha, sigma proves alpha and sigma proves not alpha. Therefore, sigma is provably stronger than sigma union alpha and not alpha. I think we already used this notation. This means that this guy can prove anything in this set can prove anything in this set, which in particular is stronger than the set containing alpha and not alpha. Right? So sigma definitely can prove everything in sigma. We assume that it can prove both alpha and not alpha, so it can prove everything in this set. This is a subset. So this set can definitely prove everything here. Right? But we already seen that alpha, not alpha, proves beta for every alpha and beta. So sigma proves beta for every beta. Violating, I mean, this is here a contradiction. Contradicting our assumption here that there was some beta that it didn't prove. So if it can prove for some alpha, both alpha and not alpha, it can prove any beta. Therefore, it's not consistent by the second definition. And if it can prove any beta, then it can also prove any alpha and not alpha. So inconsistency according to the second definition implies inconsistency according to the first. So the two definitions are equivalent. Okay, so we have this nice notion of consistency. Okay, now how can I show that a set, how can we show that a set is consistent? I can ask you, okay, let's think a little bit about this notion of consistency. What is, let sigma be a subset of sigma prime. The consistency of which of them implies the consistency of the other? Is it easier to be consistent when you are smaller or when you are larger? Easier to be consistent when you're smaller. That's the first thing that any investigator learns. You let your suspect talk. The more they talk, the more likely they are to contradict themselves. Right? So the bigger the set of statements you make, the more likely you are to become inconsistent. Okay, so in this case, if sigma prime is consistent, then so is sigma. Because consistency is about not being able to prove something. No matter which of the two definitions you pick, it's about not being able to prove. So if when you're bigger and you cannot prove, of course you will not be able to prove if you're smaller. So what is the, if we have any consistent set, which would be the, for sure, if any set is consistent, which is the set that should be consistent? What? The empty set, right? So corollary, if any set of WAFs is consistent, then in particular the empty set is consistent. So the whole notion of consistency wouldn't make sense if the empty set was not consistent. But is it? Can you show me that the empty set is consistent? What? It doesn't imply nothing. We already saw that from the empty set, it doesn't imply nothing. I mean, from the empty set, we saw that we could prove alpha arrows alpha. And from the empty set, we saw that we could prove not alpha arrows alpha. Maybe from the empty set, I can prove everything. How do I know that I cannot? You see, that's the question. So my question is the empty set consistent? That's the first thing we have to check to make sense out of consistency. Yes?
That's true because we proved earlier that our proof system can only prove true things. So
right.
Thing and it's
right.
And the opposite of the thing cannot both be true.
What is the exact meaning of true? We proved something stronger. Not yet, so we proved it. So now we have to rely on a theorem that we even gave it a name, which was called the Soundness theorem. What is the Soundness theorem? The Soundness theorem, just remember what it was. It stated that if I can prove alpha, then alpha is a tautology. And now I can give you an example of something that I cannot prove. Can you now give me an example of something that we know that we cannot prove? What? What is null alpha? Not which alpha? I mean, you have to give me an example of a concrete formula. Yes?
Yeah. Propositional variable.
Propositional variable. So in particular, the empty set cannot prove P, since P is not a tautology. Okay, so we use the soundness to show that there is something that we cannot prove. And if there's something that we cannot prove, then the empty set is consistent. Now, what will be the least consistent set? Everything. And is it consistent? Why not? Because you can prove everything which is inside your assumptions. Sigma can prove everything in sigma. So if sigma contains both alpha and not alpha, it can prove both of them. Okay. So we know that there are consistent sets, and we know that there are inconsistent sets. Right? So let us take a step backwards and see where we are in our the big picture of our discussion. So we have syntax and semantics. And let's try to remember where we are. So we started the course by playing in the syntax field. We had a definition of what are well-defined formulas and algorithm to check whether a formula is defined and so on. We had all kind of games. Is this a formula or not? And in the semantics, our first step was to talk about truth assignments. And then we have notions like alpha satisfiable, and we extended it to sigma is satisfiable. And we have alpha is a tautology. And alpha logically implies beta, and sigma logically implies alpha. And all of these were semantics notions. And we had here also the compactness theorem. And then we went back to the syntax. And in the syntax, we started talking about proof systems. So we had this notion of alpha is provable. We had a proof system, which was completely syntactic. And then we had the notion of alpha is provable, or sigma can prove alpha. And now we also have this notion of sigma being consistent. And now the next step that we want to do is to begin to make ties between the two columns. So what we already know, what do we already know? Which ties between the two columns have we already shown? Yes?
For example, if alpha is provable, then it's tautology.
Right. So, for example, we showed this implication. I don't have colored chalk, but we showed this implication. If it's provable, it's a tautology. And we also proved this implication, the extended soundness theorem. So that was soundness. That was the soundness theorem. And I want to draw more connections between the two sides. So the next connection that I want to draw is between being consistent and being satisfiable. So now I claim that, so now we are in this game of making ties between the semantic column and the syntactic column. So the next statement that I want to make is that, so here we have a very easy theorem. Every satisfiable sigma is consistent. So how are we going to prove this?
Generalized induction.
What? No, because you see, right, so I needed to add a caveat. I mean, it's not the answer to every how are we going to prove, but only how are we going to prove that are a property of something that is a set, inductively defined set, right? So, but the proof is much easier than generalized induction, right? We will go by way of contradiction. We assume that sigma is inconsistent. So, by way of contradiction, assume sigma is inconsistent. And we can use either of the two definitions of consistency. So I will use the first definition. So for some alpha, both sigma proves alpha and sigma proves the negation of alpha. This is the way to violate the first definition of consistency. Now I want to show you that it's not satisfiable. So do you see how can I proceed now using the tools that we already have? Yes?
You pick an assignment that should satisfy sigma and evaluate alpha and I-alpha for that assignment.
Right. I'm going to use now the soundness. So if, you see, I assume that sigma is inconsistent. I want to show that it's not satisfiable. So if sigma is satisfiable, since sigma is satisfiable, because, anyway, assume sigma is inconsistent. I want to show it's not satisfiable. So if it is satisfiable, what does it mean? It means that for some, just the definition of satisfiability, then for some truth assignment V, V satisfies all WAFs in sigma. Now, by soundness, from this assumption, I can get sigma logically implies alpha and sigma logically implies not alpha. So V, for that assignment V, we get V of alpha equals true and V of the negation of alpha equals true, violating the truth table of negation. So we got our contradiction. Or in other words, we showed that if it is not consistent, then it is not satisfiable. So this is a cute observation because, okay, so now we have another arrow in our table. Now we have another arrow in our table that consistent implies satisfiable. No. Don't let me fool you. I mean, catch me before I catch myself. Satisfiable implies consistent. That's what we showed. If it is satisfiable, it must be consistent. Doesn't look like an arrow. Satisfiable implies consistent. So this is kind of useful because now if I ask you something, is the set sigma equals the set of all pi arrows pj such that I, j are natural numbers? Is this set consistent? So if we just rely on the definition, it's going to be very difficult, because we will have to show that you cannot prove some alpha and the negation of alpha just based on this, or that there is some beta that you cannot prove from this, which seems very difficult. But with the tool that we have now, in order to show consistency, all I need to show is that it's satisfiable. So by the last claim, by our previous theorem, it suffices to show that sigma is satisfiable. And this is very easy. Because to show it's satisfiable, I just have to give you some truth assignment. So which truth assignment will satisfy all the formulas in my sigma? All true. They're all true. So for example, the all true V satisfies every member of sigma. So now we have a cute tool to show that something is consistent. Still, we don't have a good tool to show that something is inconsistent. So to show it's maybe I give you sigma which is inconsistent. If I gave you a sigma and ask you, is it consistent or not? So you can say, okay, if it's satisfiable, it's consistent. Otherwise, I mean, how do I show it? So what we're going to do is we're going to reverse all of those errors. We're going to show that all of those errors that we have there are if and only if. That actually the syntax and the semantics completely match each other. But before we do that, okay, so that's our goal. That's where we are aiming to get to in this lecture. Are there any questions so far? So our goal is to get to the reverse directions of all of those statements, which is going to be kind of satisfying. It will show us, I mean, you see, all of those notions just depend on the choice of truth table, which is completely natural and obvious. Here, the notion of provability is dependent on our choice of three axioms. And you could ask, why those axioms? Why not other axioms? They look very arbitrary. But once we have all those equivalences, it at least gives us some kind of confirmation that it was not a random choice of axioms. It had some inherent truth to it or value to it. Okay, so towards this goal, we will start by introducing yet another notion. And the next notion to introduce is definition. We say that sigma is maximally consistent if sigma is consistent, but for every alpha, either sigma proves alpha or sigma union alpha is inconsistent. So is it clear why I call it maximally consistent? In some sense, if I add to sigma things that it can prove, it will not ruin the consistency. So if I want to expand sigma and ask about consistency, the only thing that will strengthen it. Right? So just note that whenever sigma proves alpha, sigma union alpha is no stronger than sigma. Namely, for every beta, if sigma union alpha proves beta, then sigma proves beta. This is by our extended monotonicity, right? So if I have a sigma and I want to make it stronger, if I add it to it an alpha that it can also already prove, I didn't make it stronger. I just wrote something which was kind of already implied by what I had before. Let us, you know what, let's just look at an example of a set that is not maximally consistent. It's a very good question because, I mean, I like the way that you are thinking as we go. Don't postpone all the thinking to the exam or something. Okay, so let's look at, can we show an example of a sigma which is consistent but not maximally consistent? Just to note that this can really be the case, okay? So here is an example. Let sigma be just, not proof, sigma be just P1 over the variables P1, P2, and so on. Then I claim that it is consistent and it is not maximally consistent. So to show it is a consistent, can you show me, so claim 1, this P1 is consistent. Can you show why it's consistent? It's satisfiable, since it is satisfiable. Now my second claim is that this guy is not maximally consistent. So for that, I have to show you some alpha such that, first of all, my sigma doesn't prove alpha. And secondly, even if I add alpha, I will still remain consistent. So can anybody come up with such an alpha? Yes?
Can't you just use P2?
Just use P2. I was thinking of P3, but P2 is just as good. So,
Use P3.
okay, so let alpha be P3. Okay, so now I want to show you two things. First of all, sigma, my sigma cannot prove, or my sigma is P1, cannot prove P3. Why is that? We need to prove it. So how can I show that my sigma does not prove P3? I'm going to apply the soundness. If it does, then it will logically imply it. And this is the easiest way to show that you don't have provability. show don't have logical implication. Because by soundness, it suffices to show that P1 does not logically imply P3. Which means I have to show you a truth assignment that satisfies P1 but doesn't satisfy P3. Yes?
Is alpha supposed to be a set? Why are there set brackets around here?
Oh, sorry. Alpha is not a set. Yeah, I can get a point for it. Okay. So how do I show this? Just consider any assignment, truth assignment V, such that V of P1 is true and V of P3 is false. Then V satisfies P1 but not P3, so there is no logical implication. Okay, so P3 is a good example of an alpha such that sigma does not prove alpha. Now what do I want to show? I want to show you that my sigma, which was just P1, is consistent but not maximally consistent. So now we are moving towards showing it's not maximally consistent. To be maximally consistent, everything it cannot prove cannot be added. Now we showed that it cannot prove P3. So how will I show that it's not maximally consistent? I can add it. So what do I want to show? Finally, note that the set P1, P3 is consistent. So I added something that was not provable and didn't violate consistency. Why is it consistent? It's satisfiable. Since it is satisfiable. So we have an example to your question, why is there anything which is consistent but not maximally consistent? We have an example. Now, you can ask me another question. Is there any set which is maximally consistent? That's a good guess. Yeah, you're right. I mean, so if I take the set of all propositional variables, it's a very good hunch that this is going to be maximally consistent. But how do we show it? Do you have an idea? Okay, so here is this nice claim that, what's your name? Han? Yeah, okay. So Han had a very good sense here. I mean, I think it's an impressive guess. So if I take sigma to be the set of all propositional variables, the set of all pi such that I is in N, is maximally consistent over this set of variables, P1, P2, and so on. Right? Because when I talk about maximally consistent, I have to tell you what is my set of variables, because otherwise you can always come up with a variable that's not in my set and tell me you didn't prove it. Okay, so first of all, to show you maximally consistent, I need to show you that it's consistent and that it's maximal. So proof Y is my sigma consistent. It's satisfiable. How do I satisfy it? Right. It is satisfiable by Vt, the all true is silent. So I know it's consistent. So now, why is it maximally consistent?
Come up with the alpha, and then you say the sigma.
Yeah, so let's try to argue. Let's see if we get stuck or not. Let's hope we are not. Okay, so why is it maximally consistent? Can we show it, or we are going to get stuck? What? So if it's maximally consistent, we have to show that whenever there is an alpha that it cannot, so we want to show that if for every, let me write it like this, need to show that for every alpha, if sigma cannot prove alpha, then sigma union alpha is inconsistent. Right? That's the definition of maximal. But now we get stuck.
Add another arrow to separate.
Yeah, I need another arrow, right. So we'll have to postpone this. The claim is true, but we'll need another arrow, because the problem is that if sigma does not, I mean, we can already, with our knowledge so far, show that if sigma does not logically imply alpha, then sigma union alpha is what? Not satisfiable, but you see, not satisfiable does not mean it's not consistent. Right. Is not satisfiable. Why? Because the reason is because this guy, we know, what do we know about this guy? Is not satisfiable. And this is because we've already met this guy and learned something about this set of formulas. The notion of consistency, maximal consistent, means whenever it does not prove alpha, then if I add alpha, it should be inconsistent.
Yeah.
Okay, so I say let alpha be such that I don't prove it. I would like to show that it's not consistent. But I'm getting stuck. Okay? So what do we know about this set of formulas? Well, we've already met this set of formulas, I think last class or the one before that. It's maximally satisfiable. And it has only one satisfying assignment. So it has only one satisfying assignment. Therefore, if it has only one satisfying assignment and it doesn't imply alpha, then the only assignment that satisfies sigma doesn't satisfy alpha. So no assignment satisfies all of them. So it's not satisfiable. Since sigma is maximally satisfiable, and therefore if it doesn't imply alpha, this is not satisfiable. So this is a discussion that we had last time. If it's maximally satisfiable, if it doesn't imply something, you cannot add it without ruining the satisfiability. Right, but the problem is that we don't know how to go from not provable to not satisfiable. We only know how to go from provable to satisfiable. But we need the other direction that we are missing here. We can go from provable to satisfiable. But to go from not provable to not satisfiable will be the same as reversing this arrow. And similarly, we know how to go from satisfiable to consistent. But to go from not satisfiable to not consistent, we will have to reverse this arrow. So for an example of a maximally consistent set, we will have to wait until we will be able to reverse some of the arrows. We cannot do it yet. So we know that potentially there are things which are consistent but not maximally consistent, but we cannot yet show that something is maximally consistent because we are still missing some of our tools. Okay, so that was just, I hope that by doing all this logical gymnastics that I'm doing here, if you are following me, I want to kind of get you practiced in this kind of game, because this is the game that I expect, one of the things that I expect you to learn from this course. So try to follow up, and if not, when you read it, you will see that it's not very difficult to follow the logic of my arguments. Okay? So we introduced the notion of maximally consistent set. We know that there are sets which are consistent and not maximally consistent. What else can we say about maximally consistent set? We don't even know if such set exists. Now, with my inclination to connect anything to algebra, maximally consistent again relates to maximally independent set in linear algebra. And in linear algebra, so we can make this connection, this kind of analogy, that sigma is consistent is kind of analogous to saying a set of vectors A is linearly independent. And saying that sigma is maximally consistent will be analogous to say that A is maximally maximal linear independent, which is the same as saying that A is a basis of my vector set, of my vector space. Why is it analogous? Because what is maximally linear independent? It's not that any vector that I will add will make it independent. It's any vector that is not linear dependent on the previous ones will make it independent. You remember? Or if any of you wants to recall the linear algebra. We said that you're maximally linear independent, or you are a basis, not if any vector that I will add will make you linear dependent, but if any vector that is not already dependent. So the dependent play the same roles as provable. And now we are going to, so this is just for analogy. Now we are going to prove a lemma which is very similar to the lemma that we had for satisfiability, and very similar to the lemma that we have for linear dependence. So let me erase the analogy. It doesn't seem to me that it appeals to many of you, so let's forget about it. And let's do the lemma that we want. And the lemma is very similar to what we did with satisfiability. And it says that for every consistent sigma, there exists a maximally consistent sigma prime, which is a superset of sigma. So this is very similar to the lemma that we saw about satisfiability and maximum satisfiability. And very similar to the lemma that we know about linear independent set. Every linear independent set can be expanded into a basis. So it's the same. And it's a very kind of basic principle in mathematics that is, I mean, I don't know how many, I was going to say, I don't know how many of you care about logic, but this is a logic course. But in the more, I mean, I hope that I will get to it in this course, but this is exactly what is called the axiom of choice, if you've heard about it. It's kind of an axiom that when they were trying to make sound foundation for mathematical reasoning, they came up with a list of axioms, and then they realized that something is missing, that with this list of axioms there are things that you cannot prove, and then they added this axiom of choice. In the beginning it was kind of controversial because the axiom of choice also implies, I mean, you add things, then you can prove things which are, you can prove most things. So the axiom of choice could prove things that are kind of dubious. But the axiom of choice, without it, we cannot prove those statements. Without the axiom of choice, we cannot prove that any independent vector set can be extended to a basis. We cannot prove that any consistent sigma can be extended to a maximally consistent sigma. We cannot prove that any satisfiable sigma can be extended to a maximally satisfiable. So we really need this axiom of choice. Why was it controversial? Because some smart guys were able to prove that from the axiom of choice you can divide you can divide a ball in three-dimensional ball into 5 pieces, and then with 3 of them, without changing their shape, just by rotating them and moving them, compose a full ball of the same volume as the first one without any holes, with just 3 of the 5 pieces. So, yeah, it has some kind of funny consequences, but we will postpone it to the part of the course where we'll feel that we already fulfilled all compulsory information, and I can entertain you with nice stories about mathematics. I hope that we will get there soon. Okay, so we have this principle in mathematics that applies to many areas in mathematics. We will prove it now for consistency. We saw it for satisfiability. And to make things simpler, so we will not need axiom of choice or heavy set theory. We will just assume that our set of propositions is countable, is this set of propositions. Did I ask you, I'm sorry about all my side comments. Did I ask about how many of you are comfortable with this distinction between countable and uncountable? And know that... What? I mean, let me ask it differently. Are there people that don't feel completely comfortable about what's the difference between infinitely countable and infinitely uncountable? Did you learn it anywhere? Okay.
Sort of heard of it. And
Sort of heard of it. Okay. So, good. Oh, by the way, I was supposed to, because I'm sorry, I mean, today I'm, anyway, let me finish it. I want to make a special lecture about this. It's not part of the course, but I think it's part of your basic education. So I would like to make a special lecture just to talk about countable and uncountable. And for me, a good time will be Wednesday, either tomorrow or next week at the end of the...
Tomorrow?
What?
What time will be hard to hear?
It probably will be difficult to book a room for tomorrow, I guess. So, well, 10 p.m., right. But that reminded me that I also owe you telling you when the tutorial is, because we canceled it and they didn't get back to me with a room. So I have to nag them. Okay, so let's plan that next week, Wednesday. Tomorrow, if I'll find a room for tutorial, I will put it on Plaza and I'll put it on the Learn and we'll have a tutorial. If you don't see it by tomorrow morning, then probably we don't have a room. Next Wednesday, we're going to have both a tutorial and a special lecture on countable and uncountable, and we'll probably do it at the end of, towards the evening, and I'll find a room for next Wednesday. Okay, so back to what we're doing. And we want to show that every consistent set can be extended to maximally consistent. We will do it over a countable set of propositions and discuss countability next Wednesday. Okay, so how we're going to do it? We're going to do it very similar to what we did for satisfiability. So here is our proof. So let alpha 1, alpha 2, alpha n be a list of all WAFs over P1, P2, Pn, and so on. So you saw in the lecture on extending satisfiable to maximally satisfiable that such a thing is possible. I can make a list. I just order them by lexicographic order. First, all the formulas of length 1, then all the formulas of length 2, and each of them is just finite set of formulas. So I just order them by length. So that will be all the formulas of length 1. Oh. All the formulas of length 1 will take me all of the list, right? Because it will be P1, P2, P3, and so on. So I cannot be so simple. So what I will do is I will say, let's first have all the formulas of length 1, all alphas, so that the length of alpha is 1, and it is over just the variables P1. And then I'll have all the formulas of length, all the alphas of length at most k, over P1 to Pk. Each of those sets, I can order them by lexicographic order, and each of those sets are finite. There are only finitely many formulas with these variables, with P1 to Pk, that have lengths at most k. So since each of them is finite, each of them uses up only finitely many of my indices. So I still have tons of indices to take care of the rest of the list. So I can prepare a list of all formulas, which each of them gets an index by a natural number. Okay? And now we're going to construct a sequence of, so let sigma 0 be sigma, and construct a sequence of sets of WAFs sigma 0, subset of sigma 1, subset of sigma n, subset of sigma n plus 1, and so on for every n. So I told you what is sigma 0, and I want to tell you what are the sigmas, and we want to make sure that they have some properties. So we are going to construct this sequence, and we want to make sure that we have two properties. So such that the following holds. One, each sigma I is consistent. And property 2, that for every I, either sigma I proves alpha I, or sigma I proves not alpha I. So let's see how we can do it, and then we will see that this allows us to construct a maximally consistent set. So we will do it by induction, but not by generalized induction, but just by induction on I. So we construct the sequences, the construction of the sigma i's is by induction on I. So we said sigma 0 is going to be the sigma that we started with. And assume we don't have alpha 0 because our sequence starts with alpha 1, our sequence here, so it's clearly satisfies our requirements 1 and 2, because we started from a consistent sigma. And now, given sigma I, if sigma I proves not alpha I, let sigma I plus 1 be just sigma I. Okay? So it's easy to see that then if sigma I satisfies properties 1 and 2, sigma I proves alpha I plus 1. Then if sigma 1 satisfies 1 and 2, then so will sigma I plus 1. Because the only thing that I need to check two things. I need to check that sigma I plus 1 is consistent, but sigma I plus 1 is just sigma I. So if it was consistent, I didn't change anything. Then I need to show that it either proves sigma I plus 1 should either prove alpha I plus 1 or its negation. But I assume that it proves alpha I plus 1. So I don't have to worry about requirement 2. So if sigma I already proves alpha I plus 1, I don't have to do anything, and my requirements are retained. Now, what if it doesn't? So, however, if, on the other hand, sigma I does not prove alpha I plus 1, the negation of alpha I plus 1, then let sigma I plus 1 be sigma I union alpha I. Now I need to show that sigma I plus 1 satisfies both requirements. So which requirement now is easy? Follows from my definition. Which of the two requirements? So my claim is again, if sigma I satisfies 1, 2, then so does sigma I plus 1. Proof of claim. So which of the two requirements follows trivially from the way I define sigma I plus 1? Number 1. Why is it consistent?
Because you added alpha I here.
Why didn't alpha I not kill the consistency?
When you come to that.
Sigma I was consistent, and it didn't prove not alpha I plus 1, so I added alpha I plus 1, sorry. I added alpha I plus 1, sorry.
Yeah.
Yeah. Otherwise, you're right. Yeah. I added alpha I plus 1. So which of the two, so let me now ask it again. Which of the two requirements follows easily? 2, right. So requirement 2 follows by the definition of sigma I plus 1. But what about 1? But why is sigma I plus 1 consistent? This is not easy. So let us argue by way of contradictions. If it is not, otherwise, sigma I plus 1 proves alpha I plus 1. Why is that the case? No, proves not alpha I plus 1. Proves not alpha I plus 1. Why is it the case? Why I could even confuse myself and write it proves alpha I plus 1, it proves not alpha I plus 1. Why does it prove not alpha I plus 1? It proves everything. It's inconsistent. Inconsistent. Sigma proves everything. Okay? But we also know that sigma I plus 1 proves alpha I plus 1. Why is that?
Because it's inconsistent and proves everything?
Yeah, but right. But because it's inside. It's inside. So what I want to show is the following, that I want to conclude I want to show that this will violate my assumption that sigma I could not prove alpha I plus 1. So what I need is, I know that, so here I need a claim, and the claim will be that the claim will be what? I want to show that sigma I already would have applied. Right. Yeah. So the claim will be that if sigma union alpha I proves not, or sigma union alpha proves not alpha, then sigma already proves not alpha. And this is for every sigma and alpha. So I don't even need this. I don't even need this. So now, right, so this is what I need to, I said this will suffice. Why will it suffice? Because now, right, so now assume we prove it, so by the claim, if sigma I plus 1 is inconsistent, then sigma I plus 1 proves not alpha I plus 1, but sigma I plus 1 is just sigma I union alpha I plus 1. So we apply the lemma. So sigma I proves not alpha I plus 1, and that's a contradiction. Oh, right. But I raised my definition of sigma I plus 1, right? That's really bad. So we said the case that we were handling that we assumed sigma I could not prove not alpha I plus 1, and defined sigma I plus 1 in this case to be sigma I union alpha I. And where the claim was that this guy is consistent. So we said if it is not consistent, then this guy can prove not alpha I. And the claim is very cute. The claim just says if in order to prove not alpha, you needed to assume alpha, alpha cannot help you prove not alpha. If you can prove not alpha with the assumption alpha, you could also prove it without it. That's what the claim says, right? Alpha doesn't help you anything and doesn't give you any evidence towards not alpha. If with alpha you could prove not alpha, you could prove it without it. And that's what's happening here. I could not prove alpha I plus 1. I added alpha I. If it became inconsistent, now I suddenly can prove alpha I plus 1. But alpha I could not have helped me. So this guy could already prove the not alpha I plus 1, which contradicts my assumption. So what we got is that we proved, under this claim, we proved that you can do this extension, a series of extensions. And if we can do this series of extensions, we will end up finally define sigma prime to be the union over all I in N of the sigma i's that we constructed, and it is not difficult to see that this sigma prime is maximally consistent. So I leave this as an assignment for you to think about. Why is this maximally consistent? Actually, I'll do it next time. Max consistent, I'll show it on Thursday. Yes?
Where in this proof did we use the axiom of choice?
Right, we didn't use the axiom of choice.
Oh, I thought you said you had to use it.
Right.
Is that in the last part?
No. The only reason I need the axiom of choice is if I want to claim it over any set of variables. If my set of variables was just pi, I in n, then everything is okay. The claim holds over any set of variables. Maybe your set of variables is the set of all PR such that R is a real number. We only limited ourselves to a set of variables that is countable, pi, which is I is a natural number. If we limit ourselves to countable sets, we don't need the axiom of choice. We need the axiom of choice to show this claim for every set. Same thing for linear algebra. You don't need the axiom of choice if your vector space is finite dimension. You need the axiom of choice if it's a vector space of infinite dimension. Anyway, we will discuss it next Wednesday with our special class on set theory.